Okay, for our inclined planes question, I'm going to start on the diagram rather than starting in the box, or rather than drawing a diagram. So I'll start on the diagram that we already have in place. And the only real force, you could argue, acting on this is its own weight. So the weight force on the box acts toward the center of the Earth. And it's going to be F weight equals mg. Let's just leave that in pronumerals for the moment. We won't actually calculate out what that is because it makes it a little bit easier to do some other things that we might need to do. Now we're interested in two forces. These are kind of virtual forces in that they're components of this force. They're provided by this force, but they actually are divided out. So we're interested in, stop trying to help please, machine. We're interested in the component perpendicular to the slope. So the component perpendicular to the slope is that one, and that's going to contribute to the frictional force. So in other words, how much force there is between the slope itself and the object is going to contribute to how hard it is to get the object to move or otherwise. So that's going to be F perpendicular. So I'll just draw two lines perpendicular as a subscript to that. We're interested in that one. We're also interested in this one, which goes down the slope. And that's the force that's going to cause this to accelerate down the slope, if indeed it does accelerate down the slope. What we want to know is, will it? And if so, how fast? And so I'm just going to call that one F parallel with two parallel lines. So we're interested in F parallel and F perpendicular. Now you'll see that we've got here, it's not a very square box, but it's a right angled triangle. We've got the fact that it's 28 degrees here, and by similar triangles, if you look at this big triangle, I hope you can see the cursor going around, and this little triangle, you'll see that they're similar triangles, so that the angle in the top here is also 28 degrees. So that's going to mean that we can actually work these out in terms of that overall thing. So let's actually work out now those two forces for a start. So F parallel or let's do them in the order that I've done them in the answers on the back. So F parallel is equal to mg sine mg cos theta. And again, it's the same old trig stuff. We're looking at cos being adjacent over hypotenuse and sine being opposite over hypotenuse, and then rearranging those. So the mass is 0.4 kilograms. The acceleration due to gravity is 9.8 meters per second squared, or 9.8 newtons per kilogram, times cos of 28 degrees is going to equal 3.46 Newton. So that's the force parallel to the surface. That's the one that's going to contribute to friction. Force perpendicular equals mg sine theta. So everything else is the same. 0.4 times 9.8, but this time times the sine of 28. And that's going to be 1.84 Newton. Right, now, F parallel is the one that's going to try to accelerate it to go down the hill. We need to figure out whether it's enough to overcome the static force of friction. We studied friction in the strange case of Cassie's burnout last week, or maybe earlier this week. But we're going to figure out whether this force is sufficient to overcome the friction. So, and for that, because it's not moving, we use the coefficient of static friction. So let's find out what the frictional force will be. Force of friction is equal to mu, the frictional coefficient, times, in this case, the normal force, which is the force at right angles to the surface. And the normal force is just F perpendicular. So we said the coefficient of static friction is 0.45, and the perpendicular force we just calculated to be 3.46 Newton. So this frictional force is going to be 1.56 Newton. That's the static frictional force, and you'll see that that 1.56 Newton is smaller than this 1.84 Newton. So its weight is sufficient to overcome the force of friction and make it start sliding. So it's going to start sliding down the hill. Okay, that's good, because otherwise we wouldn't have had to calculate the other part of the problem. We would have stopped there and said, no, it doesn't move. But in this case, it does move. And we need to know what its acceleration will be. So once it's started moving, we need the kinetic friction coefficient, not the static friction. So instead of 0.45, we're going to use 0.22. Overall, the parallel force, the force due to its weight but acting in the same direction as the slope. So if you go up and look, the object is only free to move in one direction, which is the direction of the slope. It's not free to fall through the slope if the slope doesn't break. So we're interested in what the forces are that are acting in that direction in which it's free to move. So there is this force parallel is going to have to provide both the frictional force for the kinetic friction and some force to accelerate it. And in accordance with Newton's second law, that's just going to be ma. So, and then we can use that to actually calculate the acceleration, which is what we were asked for. How fast is it going to accelerate? Let's rearrange that. So acceleration equals parallel force. It's not F11, by the way, it's parallel. I probably should have had more lines on them. Minus frictional force. Frict. Over m, if I rearrange that equation. So the parallel force we calculated to be 1.84 newtons. Oh, careful, not this frictional force. We need to work out what the new frictional force is. We're using the kinetic coefficient. So the force of friction now, moving, is still going to be mu times the normal force, the parallel force. But in this case, the mu we use is not 0.45, it's 0.22. So 0.22 times, what was that parallel force? 3.46 Newton is going to be 0.76 Newton. This is the new frictional force. So minus 0.76, I might make a line there to differentiate those two things, divided by 0.4 kilogram, which is the mass of the object that's accelerating. And if we work all that out, we will find out that the acceleration, A, is equal to 2.7 meters per second squared. So remember that 1g is about 10 meters per second squared. This is about a quarter of a g, or a little bit over. So it's accelerating, but it's not accelerating as fast as it would if it was in free fall. And that makes perfect sense, because not all of its weight is accelerating it, and it's also overcoming friction. But that's the rate at which it's going to accelerate.